Yeah, I think we can go ahead now.
Okay, good afternoon to folks west of, in or west of Saskatchewan, and good evening for those east of Saskatchewan. My name is Jeff Strong, and I'm part of the organizing team for this Congress. We welcome you to the 55th Congress of the Canadian Meteorological and Oceanographic Society, CMOS or CMOS, hosted here virtually this year in Victoria from May 31st to June 11th. Every year we have 500 to 800 scientists speak on many aspects of atmospheric, oceanographic, climate, and related sciences. We just successfully completed the third day in this two-week Congress. There is an advantage of us being forced to run our Congress in virtual mode this year, for it allows anyone across the country or in the world to participate without having to travel long distances. I'm going to ask everyone, perhaps, if you wouldn't mind, use the chat to give your name and location. But if you want to ask a question, record it in the Q&A down at the bottom of your screens. Each year, we sponsor a special lecture open to the public. And my role this evening is simply to introduce our public speaker this year, Dr. Gavin Schmidt, the director of NASA GIS in New York City. We're fortunate to have a prestigious speaker like Dr. Schmidt as our public speaker, for he's well known globally for his climate research and participation in the IPCC. We're all familiar with the acronym NASA and its role in space exploration, and GIS, G-I-S-S, stands for Goddard Institute for Space Studies. One of the trickiest parts of space exploration is taking off and landing on other planetary bodies, where you must contend with the local weather. So if you're going to explore other planets, then you'd better understand their atmosphere and climate. And you start with the planet about which we have most information, planet Earth. So NASA has a strong contingent of atmospheric and climate scientists. Dr. Schmidt joined NASA GIS in 2004 and rose swiftly to become the director from 2014 on. Just this past February, he was named the acting senior advisor on climate to the NASA administrator, who reports directly to the White House. So Gavin plays a very important senior role while specializing in the numerical modeling of climate change. The theme of this year's Congress here is climate change, risk, resilience, and response. So that's one reason why we chose Dr. Schmidt. But another reason is because he has a particular gift of being able to explain the huge complexities of climate science to a layperson in terms they can understand. He's received a number of awards for addressing the public in this way, including being named in 2004 as one of Scientific America magazine's top 50 research leaders of the year. In 2011, AGU, the American Geophysical Union, awarded Schmidt the inaugural Climate Communications Prize for his work communicating climate change issues to the public. He was named Earth Sky Science Communicator of the Year in 2011. The award news release noted his public outreach work included co-founding the climate blog, Real Climate. He regularly contributes to Real Climate, including one last month titled, Why is Future Sea Level Rise Still So Uncertain? And you can Google Real Climate, all one word, and get to the site. Gavin is also a popular speaker on TV and radio shows, including The Daily Show with Jon Stewart and The Late Show with David Letterman. He was a featured TED Talk speaker in 2014, speaking on emergent patterns of climate change. The title of our public speaker's talk is, Can Climate Modeling Keep Up with Climate Change? And so without further ado, I give you Dr. Gavin Schmidt. Gavin, take it away.
Thank you very much, Jeff, and thank you very much for the CMOS organizers for inviting me. And I wish I could be there in person with you in Victoria. It's been a while since I traveled to BC, but for instance, the TED Talk that you mentioned, that was in Vancouver, and and I have very fond memories of that part of the world. I also have fond memories of CMOS. I was a postdoc at McGill in Montreal in the mid 90s, and went to a number of CMOS conferences that I enjoyed tremendously, and I've enjoyed meeting up with a few CMOS stalwarts in the gatherings that we've had during this conference. But with no further ado, let me just start this presentation, and we'll just get right on with it. So I'm going to talk about climate modeling, and I'm going to talk about both its successes and the remaining challenges that we have. And let me be very clear, we do have challenges in understanding what is happening to the climate. But just to save a lot of time, I'm just going to tell you what I'm going to conclude, and I'm going to try and fill in the pieces as we go along. So this is the outline, and if you don't want to stay for the rest of the talk, then just memorize this and go and get some tea, and then come back for the Q&A in 40 minutes. Okay. So I'm going to try and convince you that Earth system models are continuing to get better and to improve their representations of all the different things that are happening in the climate system, and that their predictions have demonstrated their skill. And so we have a lot of credibility in these models. And so they are not just models, they are useful models. But there are many issues, some of them at the level of fundamental processes, some of them at the level of important modules, for instance, ice sheets, and how they interact with things like the atmosphere and the ocean, that are still not fully included. And that leads to particular problems when it comes to predictions of things like sea level rise. But we're already observing the impacts of climate change, right? We're seeing changes in extreme events, and they're happening faster than the models have been telling us that they're going to change. And that's a problem. And I'll try and explain why that's a particular problem. So we're making progress. We're catching up with the observations that are occurring. But the question is are we going to catch up fast enough to be able to predict what's actually going to happen before it happens? And that's obviously the goal of predictive modeling. And that remains the main challenge that we have going forward. Okay, so that's basically what I'm going to conclude. And so now let me see if I can bring up some pretty pictures of some sort. Okay, well, this is a climate model. This is an old climate model. It's one of the original GIST models that was running in the early 80s. And as you can see, this is a punch card. Some of you may remember these. Each card is a line of code, and each of the colored packages wrapped up with an old elastic band was a subroutine, and you had to put them into the machine. And if you got them in the wrong order, then the whole thing would stop, and you'd have to do it over again. We no longer use punch cards, but I just wanted to bring this up because we have been doing climate modeling for over 40 years. And so we have got quite good at it, not perfectly good at it, but we have got quite good at it. And we have a long heritage of predictions and tests that we've been able to do over those 40 years. The punch cards have gone, but the language, interestingly, has stayed the same. This is a model that was written in Fortran, and almost all of the climate models that we're running right now for the latest IPCC report, they're all still written in Fortran. That has proved its worth many times over. But if you think about how climate models have evolved, they've changed enormously over those 40 years. And it's mainly been a process of assimilation. So some of you may remember the Borg from Star Trek Next Generation, New Generation, and they would go around assimilating different species and different people. And climate models have basically done the same thing. You know, where they started off as modules to look at atmospheric circulation, and then they assimilated the ocean, and then they assimilated the sea ice, and then chemistry, and then the stratosphere, and then in the end we end up with models now that include modules for almost all of the things that we think of as being part of the Earth climate system. And you'll notice that there's ice sheets down at the bottom there. They've basically been the last things to be brought into this modeling framework, and that's really still very much at the cutting edge, and I'll discuss that a little bit as we go forward. And as the models have progressed, we've done kind of tests of these models. So AMIP, CMIP, 3, 5, 6, these are programs that all of the modeling groups around the world, including Canada and the US and the UK and France and Japan and China and Australia, where we've all kind of come together, done comparable experiments with our models, historical hindcasts, forecasts of various kinds, some of them idealized, some of them more realistic. And at each stage, we've been able to compare the models to one another, but most of all to the observations. And those comparisons to the observations are the things that allow us to say that the models have indeed improved over this time. Even as they've become more and more complex, they have become more and more skillful. So here's some examples of that. So you don't need to worry too much about what these bars mean. They're individual models, but this is like 3 generations of models. So CMIP 3 was in the early 2000s. CMIP 5 was around 2011. CMIP 6 is ongoing, and these bars are a measure of skill across temperature and precipitation patterns across the world. And what you can see is that, you know, in CMIP 3, there was a wide range. Some models had quite a lot of error. Some models were even quite good even then. And then as we've kind of moved forward, the median error in the model has gone down, and the best models have got better. But it's clear that, you know, some models are not quite as good as even earlier models were 20 years ago. That's an interesting thing to discuss. But basically, the models as a whole, as a collection, have been getting better and more skillful. I'll give you here's some other examples, like patterns associated with modes of variability, like the El Nino events in the Pacific decadal oscillation, which is a longer term process in the Pacific, or the northern southern annular modes that control, you know, what the jet stream is doing in any particular winter. You can see, for instance, in the El Nino patterns, the different generations of models, right, are all kind of marching towards the right, and they're marching towards higher correlations with the observations, right? So as the models have got better, they have both better distributions of temperature and rainfall, but also better variance, better variability, so that the weather and the seasonal variations look more accurate when you compare them. And if we take those old models and we say, well, they predicted things that were going to change mainly because of carbon dioxide, what did they predict, and how well did they do? So this is not quite a GCM. This is a slightly simpler model that was run in 1981, and you can see the black lines are what were published in that paper in 1981, and the actual temperatures have actually warmed more than were being predicted in the 1980s. The first GCM experiments that had had kind of transient forecasts were the ones that were done by my former boss, Jim Hansen, and his group in the early 1980s. And those too have been successful. They were skillful, and they are better than what other people were saying at the time. In the year 2000, we were putting together CMIP3, one of those intercomparison projects that I mentioned earlier on, and everything on the forecast side was information that they predicted without having had it happen already. And so you can see that those models have been able to predict the trajectory of global warming very, very accurately indeed. And we did it again in 2005. And these are the model results from CMIP5. And again, slight differences in what we drove them with, but again, the basic models are very, very accurate at predicting things like the change in global mean temperature, right? And we've done this many, many times. And we wrote a paper a couple of years ago that went back and found every single prediction that we could find from the 1970s and 80s, and we rated them. And we said, well, how well have they worked out? And the vast majority of them had done very, very well. And the ones that didn't, we understand why they didn't. Those projections are good, not just in the global mean, but also in the pattern of change. And what you see here, this is a very old projection from GFDL, which is associated with Princeton University and NOAA. You can see even in a very coarse model, the patterns of change are very robust. You see more warming over land than over the ocean. You see more warming in the north and in the south, and you see most warming in the Arctic. And that's not just something that was predicted 30 years ago, but it's something that we see in the observations today. If you extend it out and you have plausible scenarios for what might continue to happen in terms of carbon dioxide and methane and aerosols and all the things that affect climate, you end up with troubling amounts of change. Right, so you can see here, 1850 through to 2020, it's the observations. From 2015 onwards, they're projections of a particular model that we're working on at GISS. And what you see is that what we've done so far, we've warmed up the planet by about 1 degree Celsius, a little bit more than 1 degree Celsius, a little bit more than 2 degrees Fahrenheit. And if you extrapolate that out, and if you say, okay, well, here are some plausible scenarios, it's very easy to get temperature changes compared to that pre-industrial period of 2 degrees, 3 degrees, 4 degrees, and even higher, just by the end of 2100. And those are big numbers. Now, they don't seem like they're big numbers because we're not used to what a planet really changes its temperature by on a regular basis, but they are big numbers. And they're the kinds of numbers that nobody here is going to remember the last ice age, but the last ice age, 20,000 years ago, had ice sheets that stretched from the Arctic Ocean to New York City, that had so much water in the ice caps that sea level went down by about 120 meters. That planet was only about 5 degrees Celsius, maybe 6 degrees Celsius colder than the pre-industrial. And we are looking at potential changes in just a century that are comparable on the warming side to how cold the ice age was on the cooling side. And if you think about how different the planet was during the ice age, and then you think about how different the planet might be under a similar change going forward, you can start to see why there is so much concern among scientists for these trajectories. Now, I mentioned kind of in passing there that it was because of us, right? That's a very good kind of question, and it's one that's been answered by many groups around the world, and I'll just give you an example here of how we do it. So this is from one particular model. I'm looking at one particular variable, the global mean surface temperature, and what I'm looking at here, this spaghetti plot, is each of the different colors is a different set of things that could be driving climate. There's the temperature changes associated with those particular changes. So you can see kind of in the middle that there's an orange line. That orange line is what would have happened to temperature, according to the model, if you'd only had the changes in the solar constant. The red line is the changes that you would have had if only volcanoes had gone off. The green line is what would have happened if only the orbital wobbles had wobbled and nothing else had changed. We can compare the natural elements, so the solar and the volcanoes and the orbital forcing. We can put that together and call that the natural drivers of climate change. And you can barely see it, but it's right in the middle of that pack, and it's very, very close to zero over that entire period. But then if you look at some of these other lines, you can see that ozone pollution has caused, and that is thought to have caused a specific warming over this period, but not enough to match the observations, which are in black. You can see that there's a line that goes down. That line is due to the tropospheric aerosols, so air particulates and pollution. And if that had been the only thing that's going on, then that would have cooled the climate by a little bit over 0.5 degrees Celsius. But then you look at the line that goes up the fastest, and that's greenhouse gases. That's the changes in carbon dioxide, the changes in methane, the changes in chlorofluorocarbons, the changes in nitrous oxides. And if you put those all together, then we predict that the planet would have warmed more than we actually saw. And when you combine all of the anthropogenic, all of the human-caused factors, you get that blue line, and that blue line falls almost right on top of the observations. And then when you include the human and the natural drivers, then you end up with predictions or hindcasts that almost completely encapsulate the observations. So when people ask us, how do we know that what's been happening is due to us? It's because of analyses like this. Right? And we could do it for Arctic sea ice, and we could do it for stratospheric cooling, and we could do it for ocean heat content. And the answer is always the same. The answer is that we are to blame. The things that humans have done to the climate are driving all of these global trends over the last 50 to 60 years. But we keep going. The climate modelers, they're never happy. Their models are never perfect. It's always good to improve them. And we have been adding new features to the models. We've been adding new physics to the models. We've been increasing the amount of detail in these models. And something strange happened in this last go-round. I think as a community, we're a little bit shy about talking about this, but something strange happened, and I think it's important for us to know why that is. So CMIP 5, as I mentioned earlier, was the comparison project that ran in the late 2000s. Let's say 2010. CMIP 6 is the project that's running right now. The CMOS 6 models are much better. You know, I showed you that graph. They have lower errors, they have better skill, and they have one thing that's very odd, which is this spread here, the orange spread in this column, this spread is the equilibrium climate sensitivity. So how much that model warms if you double the amount of carbon dioxide. And that's a metric that we use basically to kind of like test out the models in an idealized setting. You double the amount of CO2 and you see what happens to the model. And it turns out that that metric is very tightly correlated to how much we're going to warm through the 21st century. It's implicated in how much rainfall is going to change as a function of the global mean temperature and the like. But what happened in CMIP6 is that the spread in this number that we didn't think was that uncertain, the spread increased enormously. Right, and it was all because of clouds, and it's particularly all because of low clouds and how reflective they are. And it turns out that we still don't know enough about those low cloud processes to be able to constrain how those clouds are going to react to increasing amounts of carbon dioxide. We also don't know exactly how much stuff there is in the atmosphere. And when I say stuff, I mean things like dust and sea salt and organic carbon and black carbon and pollen and there's another bunch of aerosols that I forget, sulfate aerosols. And you can see here, these are different model runs. It doesn't really matter kind of what each color means, but the idea that you should get from this is that they're not the same. Different models will produce different amounts of sulfate in the atmosphere, different amounts of sea salt. And then when they're perturbed, then they have different sensitivities. And the reason why we can't distinguish between those models and say, oh, one's right and one's wrong, and we can't calibrate those models to observations, is that we do not have sufficient observations of aerosols to be able to do that. And that's a huge problem for us. And it's a problem that hopefully will be alleviated. One of the new sets of missions that NASA is planning for the next decade will be a series of missions with aerosol polarimeters on board that will allow us really for the first time to get a global and long-term view of what all of these different aerosols and particles are doing. But until then, we have a lot of structural uncertainty and we have a lot of variance across the models. And that makes a difference. So this is the amount of cooling that you would get, or the amount of cooling driving that you would get from two different estimates of how you should do aerosols. One of them, with exactly the same emissions as the other, says that the cooling effect of aerosols has continued and has not slowed. And the other one, the matrix model here, suggests that, in fact, it's actually going down, and over the last 20 years, the cooling effect from aerosols has gone down. And that makes a huge difference as to whether we expect or how fast we expect the rates of change of warming to be happening right now. Because if I take away something that's cooling the climate, that's an equivalent to warming the climate by adding something that's a warming factor. But let me give you another example of where we are in trouble. Now, one of the nicest results that we've seen in the last few years when it comes to sea level rise is what's called the closing of the budget. Right? We know from independent measurements how much mass is coming into the ocean from the ice sheets, from the mountain glaciers, how much mass is coming out of groundwater supplies, how much mass is being kept in by reservoirs and embankments, how much the ocean is expanding because it's warming up. And when you take all of those different elements that we have independent evidence for, and then we compare it to the independently measured sea level change, from 1993, and we have independent measurements of that from satellites over that entire time period, what we find is that they all add up. Right? There's no missing source of sea level rise. We know where all of the elements of sea level rise are coming from. Right? That's a remarkable feat. But when it comes to the global models, and I mentioned that they were just starting to bring in the ice sheets, right? You can't do this with a GCM, because it turns out that a whole bunch of these components are not included in any of the CMIP6 models. The mountain glaciers, it turns out that they're too small to be included, right? And the peaks are too high. They're not part of the domain of these models. The loss of mass from Greenland is not included because we don't truly understand yet how the coupled dynamic ice sheet models are supposed to work properly with the GCMs. In Antarctica, we're not including that either. And so if you take all of these things and the total land water, we're not really tracking the groundwater in the system. We're not really tracking the building of reservoirs and dams. And so these things are not included. And so when you look at sea level in a climate model, you're only looking at half the story, right? You're only looking effectively at the thermal expansion part. And so we can't use the models that we spend so much time building to give us on their own credible predictions of sea level rise into the future. And these are big numbers, right? These are the changes in ice thickness from Antarctica and Greenland measured from gravity measurements. So they're actually measuring the mass change over these ice sheets. And you can see that Greenland is losing mass almost everywhere around its coast. It's gaining mass a little bit in the center, whereas Antarctica is mostly losing mass in the West Antarctic region. And these are not small numbers, 148 billion metric tons of water per year, 250 billion metric tons from Greenland per year. These are noticeable and large impacts on sea level. And yet we don't yet have, couple models that include all of these processes. And we know that sea level is a problem. You don't have to go to Venice to know that sea level is a problem. But if you do go to Venice, and I recommend it, it's very pleasant when it's not underwater. What you see is a very nice set of records, which actually go back. This is to the 19th century, but they have records that go back to the 16th century of flooding events in the Venice Lagoon. And what you can see is that things that were a 1 or 2 event per decade occurrence are now a 5 times a year occurrence, right? That's a massive change. Now, partly this is because of subsidence of the city itself that has mainly been arrested, but a lot of this is due to sea level rise. And if you go to other places around the world, Miami, for instance, and you ask, or up and down the East Coast, and you ask, are we seeing increases in high tide flooding? The answer is yes, and we're seeing exponential increases in high tide flooding, which is exactly what you expect when there's a mean change in the sea level. But then, there are high tides and storm surges that just lead to an increasing number of thresholds being crossed. We're also finding human fingerprints on extreme events that are detectable in many cases in many parts of the world for many different kinds of events. This is a summary of that put together by Carbon Brief, and each of the dots here is a different extreme event that has been examined, and they're different kinds of extreme events. Some of them are extreme rainfall, some of them are extreme heat, some of them are intense precipitation, marine heat waves, atmospheric anomalies of various things, cold events. And what they're doing here is they're asking, is the is this event more or less likely if we take away the climate change that's due to humans? And in every one of those red dots, what they found is that this event was either made more frequent or more intense because of human built or human caused climate change. And the few places that you can see where there are blues, that's where there's no human influence has been found. And there's a pattern here. So it turns out that changes that are associated with heat or thermodynamics are increasingly and predictably now being partially attributable to human activity. Whereas events that are more dependent on atmospheric dynamics or just particular configurations of the circulation system, what we're finding there is that we don't yet detect a change in those extreme events. But we are seeing changes in extreme events almost everywhere we look. There's still a lot of work to be done there. We're not looking at every single extreme event. Like, so which ones are we picking? How do we define an event? It turns out that the attribution depends a little bit on exactly how you define any particular event. And where we haven't got long observational trends, it's harder to say that something new is happening. But one of the key things in this extreme event attribution task is that you need to evaluate the climate models. Do they have all of the features that are important for those events? Do they have all of the drivers that are influencing those events, whether it's from irrigation or aerosols or changes in groundwater or whatever it is? Do those models include it? And a lot of times the models don't include the right forcings, and they don't have sufficient skill at predicting the extreme events that you're most interested in. But where they do, we can move forward. And then we can start to ask those kind of questions. How many times is this going to happen in an anthropogenic world, in an anthropogenically warmed world, compared to a pre-industrial world? And then that gives you that ratio that allows you to say that something might be happening, 5 times more often than it was. There was a very, very good paper that just came out maybe a couple of weeks ago by Gert, Jan van Oldenburg and colleagues, and their website there, www.worldweatherattribution.org, really goes into some detail about how we're doing in terms of attributing changes in extreme events and why you would want to do it. I heartily recommend it. Oh, what happened there? Yep. Okay. But we know that these things are increasing, right? We're seeing changes that are unprecedented, right? We're seeing 100-degree Fahrenheit days in northern Siberia associated with not just heat waves, but also smoke events and wildfires. We're seeing changes in hurricane intensity and frequency in places like the Caribbean, and that has direct impacts on the Caribbean islands, but also the Gulf Coast, Florida, Mexico, and the like. But these things are not all represented, not at all well represented in the models either. But we can put these in the models. This is basically just eye candy, right? This is a simulation of the summer of 2017, which some of you, if you're in BC or Alberta, will remember as a particularly smoky event. You can see the smoke there coming from wildfires in British Columbia and the like. That smoke event, it was visible across North America, even to Europe. And then you can see, you know, some of the extreme hurricane events that we had there. You just saw Harvey, and now you're going to see Irma, and now you're going to see, you know, some of the Jose. That's it. You can see them. This is a reanalysis, so it's not a predictive model in that sense. It's taking in all of the information that we had at the time, and then trying to make a physically consistent map of everything that was going on, and we're trying to keep this complexity going. You can see like dust storms coming off the Sahara there, but all of these things are interacting, right? The dust is interacting with the storms, which is interacting with the smoke, which is interacting with people. And these kind of multiple kinds of extremes are happening all the time. And it's very, very important that we know and are able to predict how they're going to change in the future. Model development is a continuous process. You know, we take the inputs from the model, the land surface, the topography. We kind of update those all the time. We use the satellite measurements to improve our understanding of small scale processes like rainfall or cloud formation. We're using, you know, the state of the art machine learning to calibrate these models so that they have the best simulation of the present day climate that we can have them be. And then we spend time evaluating them and seeing how much better than they are now than they were then. And then we keep going around because they're never perfect. But even though we're doing all of those things, even though we're trying to make them better, what happens in the future doesn't really change at the large scale, right? The different choices that we have, from aggressive mitigation, like really pulling down emissions, kind of doing as good a job as we can in trying to keep to the Paris Agreement targets. Or if we decide to burn it all, we take the tar sands and the oil shales and the methane hydrates and the oil and the coal, and we burn it all. We have those choices, but those changes that you're going to see are massive. Even under aggressive mitigation, you're talking about another degree of warming. You're talking about another move along that bell curve of extreme events when it comes to heat waves, when it comes to wildfires, when it comes to sea level rise. These choices that we have as a society, these are real, and they don't go away in 5 years' time or in 10 years' time. They have to be choices that we continually commit to as we move forward through this century. I bring up this photograph because when I'm feeling a little despairy about this situation, it reminds me that even fish, you know, in the midst of total devastation, and this is after a big flooding event, after Hurricane Florence, a lot of fish were swept onto the land, and then the water went away and the fish were left behind. Even in the middle of an existential crisis for all of these fish, one fish is still so busy trying to eat another fish that it isn't paying any attention to the fact that everybody is going to die. And I worry that too many people are like this big fish. And the current global scale climate policies are not consistent with a sustainable future. And that worries me a lot. Nonetheless, in the last year or so, people's political will has been renewed. People's targets, society's targets, countries' targets and pledges have been ratcheted up. And we are getting closer, not there, but we're getting closer to having the political will to prevent the worst of future climate change. but we have to turn those words into action. And one of the most important things that I think about as a climate scientist, as a communicator, as a public citizen, is this phrase or this quote from Sherwood Rowland. Now, Sherwood Rowland, some of you may know, won the Nobel Prize for his work in discovering the chemical reactions that led to stratospheric ozone depletion. And many years later, and many years of activism later, he was quoted as saying, "What's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is stand around and wait for them to come true?" And we are in that exact same spot now. I am making predictions. We as a community are making predictions, and we are making predictions that we do not want to come true. And so the normal incentive structure for a scientist is inverted, right? Normally you predict things and then you're so happy that what you predicted was right because it means that you've been able to grasp some element of truth from the universe and kind of make it ours and then use it appropriately. And we're supposed to be glad about that, right? Scientists are supposed to be happy when their predictions come true. But we're not happy when our predictions come true because we do not want them to come true. And so we are in this very, very odd ethical dilemma that is a little hard to deal with sometimes. But like I said, you know, we are I think on the cusp of being able to look at our predictions that we have made and say, no, they will not come true. And that will be a very happy day indeed. Thank you very much.
Thank you so much, Gavin. I'm going to look at the questions and just give some of them to you.
Sure.
An anonymous person said, the maps of sea ice thickness in Antarctica and Greenland show that the inland sea ice tends to be becoming thicker. Why is this?
Well, that's not sea ice. That's glacier ice. It's an ice sheet, and it's becoming thicker because as the planet is warming, there's more water vapor in the atmosphere. That water vapor comes down as snow in very cold environments, and so the snowfall is increasing in the center of the ice continents in Greenland and in East Antarctica, and so they're gaining mass in the middle and they're losing mass around the edge, and the losing mass is winning.
Okay, thank you. A second one from Frank Siglenix. The Paris Climate Accord has the goal of limiting the change in global mean temperature to 2 Celsius. And recently the G7 countries met and agreed to keep the rise to 1.5. I don't think you're going to answer this very happily, but I know it is hard to predict, but what do you think the eventual change in global mean temperature will be?
I really don't know. It's very much dependent on what we do, and humans are the least predictable part of this system. You know, I think we'll probably hit 1.5 sometime in the next 10 to 15 years, but whether we stay there or it comes back down again, or it kind of stabilizes at like 2 or 2.5 or 3, really depends on what we do, and it relies, I mean, like getting off those paths, staying below those targets, really require us to reduce emissions of carbon dioxide and then the other ones to effectively zero by around 2050. And if we're not on that trajectory, then we're just going to blow straight past those targets.
I'm going to add a little bit to that. If we talk about 1.5 C globally, it's probably higher on land and higher at high latitudes. About 8 years ago, a paper was published by people in Environment Canada Climate Division, and the mean in about the last 84 years, the mean surface temperature in Canadian landmass was 1.7 C, and it was about above 60, it was about 3 degrees Celsius. So
yeah, I mean, in Canada, it's warming at about twice the global mean rate, and in the Arctic, it's warming at about 3 times the global mean rate. Yeah, so the shifts that you're seeing in the archipelago and in Nunavut and Hudson Bay, I mean, those are changes that are very, very noticeable to folks there right now.
Here's another one from an anonymous person. What do the limitations of global scale models imply about dynamic downscaling, given that regional climate model data are increasingly being used for regional climate change impact assessment?
Yeah, no,
the bias correction of Earth system model data sufficient?
Well, it may not be sufficient, but it's all that we have at the moment. And we have statistical ways of doing downscaling. We have dynamical downscaling. I would be I would look at those things with a skeptical eye. There are some things that I think that they do well, but there are other things where it's not quite clear that they're telling you anything different than you were getting from the large scale regional, the large scale global models. So that's very much a cutting edge issue. I don't think that's really going to be resolved until we get the global models to have the sufficient resolutions that you don't need to have the downscaling to the local things. But that's going to be a while coming. So yeah, I can't be super optimistic there. But I'm involved in a number of different projects that use regional climate models, and for a lot of things they do a good job. So we just need to be a little bit skeptical of everything that comes out of them.
Here's one from Kendrick Sharp, who lives in Florida. As someone who is 20 years old, what advice do you have for someone my age? Should I be moving away from the Florida coast?
Well, I mean, I like Florida. I like the Florida coast, and so don't move away, but maybe don't invest a huge amount of money in the beachfront property. Rent, perhaps.
Here's one. The climate prediction for 2100 shows Argentina gets cooler.
Yeah, that was just.
What can explain that?
Yeah, I have no idea. It's that's a quirk in those model runs, and I have investigated. I really don't know what's going on there. What it shows is that, even if the whole world is warming on average, there are still going to be places that look a little cooler. That there's enough chaos in the system that you can have places that would have even 50-year trends towards cooling, even while everything else is warming, and that's still consistent with the overall pattern of change that we're predicting.
Here's another one. Given the pace of human mitigation, what geoengineering solutions are viable, e.g. stratospheric aerosol injection?
So that's an interesting question. Viable. So you can break that down into a number of different elements. There's physically plausible, right? So solar geoengineering is physically plausible. It's just effectively repeating what volcanoes have done naturally many times before, but viable as a human endeavor, that's a very different question, and that revolves around questions of geopolitics, governance, ethics, and morals. And I find it very hard to see how that could be maintained sustainably in the face of normal geopolitical tension. Let me give you an example. One of the things that we expect to happen with geoengineering is a reduction in the Indian and Asian monsoons. What happens the first time that there's a failure of the monsoon under a geoengineering scenario? It might not have anything to do with it, right? But it might just be random, that something that just happens. But now you have a situation where you have nuclear armed states who might think it an existential crisis to stop the geoengineering effort from continuing. How do you deal with that? How do you deal with the fact that we can't even all agree to reduce emissions, right? And let alone like set the perfect temperature for the world. I think that geoengineering has some very fundamental. There's a democratic deficit that will be increasingly evident if this was ever done. That would mean that it was not sustainable over the decades to centuries that you would need it to be working while we were continuing to reduce emissions. And if we're not continuing to reduce emissions, it's insanity.
Good. Are there factors shown to cool the Earth? Do you think it will be necessary to adapt to a hotter Earth, or is there potential for cooling to occur?
So outside of solar geoengineering or massive amounts of volcanism, there is no cooling on the horizon in any short time scale. So there will have to be, there is right now, adaptation to the current changes, and one can anticipate adaptation to changes to come. And that's, and if you're planning for a city on the coast, if you're thinking about heat stress, if you're thinking about wildfires, then you absolutely need to be thinking about adaptation right now, both to what we have done already and to what will come. The mitigation that we're trying to promote is really so that you don't have to adapt to an ever-moving target, which becomes impossible and extremely expensive.
Another question from Julie Putko. I'm paraphrasing it because it's quite long, but the idea is that if we are lucky enough not to see the dire predictions come true, then because the predictions would be technically wrong, would climate scientists be discredited, and then we may go back to our old ways?
That would be a great outcome. I'm happy to take as much discredit as would be required to avoid those worst outcomes.
This is a very long paragraph. I'm not sure. I think the example of not knowing enough to predict sea level rise is very instructive. Other human processes like soil degradation could have significant impacts on water retention, energy balances, and dust.
Absolutely.
Very little are done on including human processes in the soil layers of the system. How can we better focus on some of these other human impacts and include them in our analyses?
Oh, that's an excellent question, and I've focused here on the climate aspects, but any kind of policy really needs to be a joined up policy that includes things like soil retention and erosion and reforestation and natural solutions to mitigating the impacts of sea level rise using coastal marshes and restoring degraded land systems, for instance, in the Mississippi Delta. All of those things where they're regionally relevant, they have to be absolutely part of the conversation. And we can't just think of the climate as being separate from all of those things. It's an additional feature that perhaps people had not really thought about until relatively recently. But it's part and parcel of a very complex system that involves many different human activities and many different human relationships to the land and the planet.
Ken, there's quite a few questions in the comments too.
I think we're probably, yeah, I realize, I see that now. I was hoping that wouldn't happen, but I think probably we can only take a few more. And one person that wants to know if you take interns. He's at University of California, Berkeley.
Oh, we do, yes. Interns.nasa.gov. You can apply there. It's a centralized thing, and they'll find you a mentor. And we've been doing it the last year and a half. We've been doing it fully remotely, and so people can be anywhere and working with us. So yeah, go ahead and apply. So
I'm just going to go to the two more questions. This one says there have been very scary stories in the media about abrupt climate change, permafrost thaw, Arctic sea ice melt, the quick slowdown in AMOC. How would you respond to these types of news articles? Sort of the tipping points, I guess.
So I mean, there are a lot of thresholds in the system. And there are many thresholds that are local that are important. But there's a lot of loose talk about tipping points as well, and there's a lot of conflation of things just changing with some kind of catastrophic change. So the Arctic sea ice, there's no evidence that I've seen that suggests that that's actually any kind of tipping point. If we cool down, it would come back. I mean, it doesn't keep on going even after you stopped changing it. Now permafrost, permafrost is a relic of the last ice age in many places, and is degrading quite a lot, and that has increased over recent decades. That's probably not going to come back. So there are tipping points there. But again, if we stabilize the temperature, then we would stabilize the permafrost as well. Now AMOC, the North Atlantic, that does seem to be more of a classic tipping point where you push it and then it kind of finds a new state. But we think that it's decaying a little bit, but I don't think anybody thinks that we are close to that tipping point just yet. Another century of this, I think that would be a different story. But we're not going to see a day after tomorrow scenario. If any of you remember the only movie in fact, the best movie that ever had a paleoclimatologist in the leading role, and of course the worst movie that also had a paleoclimatologist in the leading role, because of course there's only been one movie with a paleoclimatologist in the leading role. Yeah, we're not going to see anything like that, thankfully.
There's one other comment that I thought was interesting. It's about how the models tend to be agreeing closer now with each other, and is that maybe giving us a false sense of security? Maybe all the models are missing some key things, so they're agreeing more, but not necessarily with what's going to happen.
I don't think that that's the case. I think the latest generation of models are disagreeing amongst themselves more than they used to, and that's because people are putting in more and more details which have more degrees of freedom that have not yet been constrained by the observations. And so the notion that all of the models are kind of converging on one thing, and then we'll be blind to the fact that they're all systematically wrong. I think that is unlikely to happen. And we're very, very, I mean, as a community, we're very, very aware of the things that they have in common that we think are imperfect, like, you know, how they deal with ocean eddies. That's one thing that all of the models have in common, and yet we know is not right. How they deal with the ice sheets, again, one thing that they don't all include, and we know that is a problem. So you know, we're working very hard on those elements where we think that the models all might be agreeing for the wrong reason. But in fact, the models are in fact diverging. I would expect that they would come back together as we constrain cloud processes a little bit better, as we constrain aerosol processes a little bit better. But that's perhaps to come in the next round.
Okay. Well, here's another question related to climate mitigation. The CRISPR, that's that you know, the genetic thing where you can put in and pull out bits of gene. The CRISPR community moved quickly to establish a bioethics oversight body. Is there any talk in the climate community of forming a geoethics oversight body?
So people have talked about such a thing, but I think that that's mainly as an academic exercise. But I think that would be good. But I think that the real ethical issues don't lie with the scientists so much as with the policymakers. And getting the policymakers to sign up to an ethics pledge, I think, might be a little bit too optimistic.
Well, I guess it's not quite fair to you, given that you won't get a chance to ask this person questions. Andrew Weaver was our first plenary speaker, and he's asking you, are you able to articulate your expectations for meeting the Paris Agreement targets, or not meeting them?
Well, the targets are long-term targets, and I think that you know, we could be kind of over-focused on, you know, what 1 year does or what 1 decade does. You know, I mean, it's possible that we could turn the corner, and, you know, and we would look back and we'd see that, you know, the 2040s or the 2050s were in fact the peak warming, and that we would then go back. We would cool slightly to the end of the century. That it's not. I wouldn't say that was an expectation, but it's certainly plausible. And so I don't really know how to answer that. I'm not. Predicting how societies are going to react is not something that's really conducive to probabilistic thinking. It's too contingent on people and politics and a little bit of luck. So I don't know how to respond to that. Sorry, Andrew.
Here's one, Hugo Beltrami.
Hi, Hugo.
Could you comment on the energy balance of the Earth system models and the tuning that is applied to some processes?
Well, the energy balance of the models, you know, what we're trying to do is we're trying to measure all of the energy fluxes within the system. And so we want them all to conserve energy, which means that at equilibrium, they have to have the same amount of energy going in as they do going out. And my model certainly does maintain that. And I would hope that that the other models spend a lot of time worrying about those kinds of things too. But the models are, of course, calibrated to the to the present day world. We don't have, you know, first principle calculations from, you know, from conservation of mass and quantum mechanics all the way up to cloud processes. So there are a number of things where, you know, we have created phenomenologically consistent formulations, but there's some wiggle room that we can tune the models to get a better estimate of low cloud in the Pacific or something like that. As I briefly mentioned as we were going through, we're now using a machine learning technique to try and explore all the dimensions that we can of those degrees of freedoms all at once. To try and build models that are better calibrated to the observations while still conserving energy, yes, and they do give better predictions of things like cloudiness and radiation and temperature. It's yet to be demonstrated that they give better predictions going forward, but I think that we'll be able to demonstrate that soon, he said, hopefully.
Do you have another question? Do you think that given that the progress of the models where they are now and your relative confidence in them, do you think there's a need for the Intergovernmental Panel on Climate Change to continue to put out its assessment reports?
That's an excellent question. Yeah. So the original IPCC reports were basically there to alert the governments to the fact that that human climate change was both at the beginning detected and then attributed and then projected forward. And I think that they've done an admirable job there. I think you could make a good argument that the setup for IPCC as it stands right now is not necessarily optimal to helping governments make good decisions about mitigation or adaptation. I think that there are other models that exist. For instance, the United Nations Environmental Project just had a big report on methane where they say, well, here are a bunch of policies. You scientists tell us what the impact of imposing those policies would be. And then it was like, oh, well, the climate would cool and the air pollution would go down and you would save this amount of money and these number of people would not die and this kind of economic benefit would result. And I think that those kinds of, kind of policy maker driven questions and then responses from the scientific community are better suited to this particular moment than the scientific community getting together and just telling everybody what we think is important.
Okay, I think this will be the last question. How can climate scientists, because it's part of our whole Congress theme, is how can climate scientists amplify their voices for climate action by partnering with other scientific disciplines such as public health and the behavioral sciences?
I mean, this is not a topic where people are not aware of what's going on. I mean, we're getting requests for collaboration from people all across the world, from all sorts of different disciplines or practices, asking for help and for information or wanting to help. And if you're talking to regional policymakers, city planners, they're already dealing with very multidisciplinary, transdisciplinary issues. And so this is already happening, and I think we need to be open to listening to those different perspectives, and engaging in the kind of co-production of a new kind of information that comes out of that. Sometimes it's not so comfortable for people that just want to look at radar or they want to look at aerosol particles in the lab. Maybe it's not necessarily for them, but for the people that are wanting to take their science and their community and make more of a difference to people and to crops and to public health. We should be coming out of the lab. We should be coming away from our computers and joining with other groups who are concerned, perhaps with a wider range of issues than just the specific issue of climate. But these things are all connected in very fundamental ways. And I think that, you know, if we you know, with a little humility, if we come out and say, well, we know things, we know certain things, we don't know everything, and we're very interested in learning how what we know fits in with what you know and what your practice is, then I think we can do some great stuff.
Just one last question. Often if scientists are urged to advocate on the, you know, and then they're accused of not being neutral. Do you have any final words on that?
Yeah, it's basically nonsense. So anybody that becomes a public scientist and who is involved in this discussion, you are an advocate. You are putting your normative values on the line, and you have to be clear about what it is that you're advocating for. Because if you're not clear about what it is that you're advocating for, then people will make up things that they think that you're advocating for, and then you spend all of your time trying to be on the defensive. But the fact of the matter is that we are citizens. We do have values, and we do have preferences. And when we pretend that we don't, and we pretend that all of our interventions in our science is because of some objective approach that only we are privy to, it's unconvincing, because it's not true. And so I think we need to embrace the fact that we are citizens and scientists, and while we should strive to make our science, the science, as objective as possible and as replicable as possible and as useful as possible, we have to recognize that why we're doing what we're doing, why we're talking about it right now, why we're out here collaborating with everybody, those are value-laden statements, and yes, we are advocating, and we just need to be very clear that we're doing so, and what it is that you're advocating for, because not everybody is advocating for the same thing. And and if you're advocating for a higher level of conversation, if you're advocating for a very specific issue associated with the Amazon jungle, just say what it is that you're advocating for, and own that. Because you actually build credibility with people that are listening to you if you're honest and authentic about what it is that your values are, and how your knowledge as a scientist and your values influence what it is that you should advocate for.
Well, thank you, Gavin. I think we'll take that as an opportunity on behalf of everybody in CMOS to thank you for a great talk. And I want to thank everybody for their very thoughtful questions. And I hope I gave justice to the questions. Some I skipped just because we had so many. So again, Jeff, thanks so much.
And thank you very much.
We'd clap if we could.
You can clap. Thank you. There we go. Thank you very much.
Thank you.
Thanks, Gavin.